As we work on this handout, I strongly encourage you to attempt to answer each of these questions on your own before watching me do it. Really, my going through the process of solving or answering these questions is really just in case you want to double check the answers that you come up with yourself. I think all of these, I do intend this to be doable on your own. So with that said, go ahead and pause the video here and see if you can answer questions, I think A and B. Okay, so hopefully you have an answer for A and B already. For A, on what intervals is f of x increasing? So f of x is the solid graph here, and increasing, right, we're just looking for places where it's going up as we move rightwards. And it looks like over here, so I'm going to color where it's increasing red. Over here it's increasing because it's going up, and it continues going up all the way to, looks like this top point here. And then it stops increasing because as you move rightwards, it goes down instead of up. So then it's going down all the way to this bottom spot here, and then it turns around and it starts going up again as we move to the right. So here it's increasing more, like all the way to the end there. It looks like it's increasing. So just to write down what these intervals are, I'm going to act as if the trends established at the ends here just continue. So it looks like it's increasing for x values from minus infinity all the way up to this top spot here. Looks like it's at x equals -1. And then it's also increasing, looks like, from this spot, which is 3, all the way off to the right. So that's to plus infinity. And to put these two intervals together to indicate that it's increasing on both of these intervals, we use the union operation, which sort of indicates that it's both of these intervals. All right, so for decreasing, well, remember decreasing means as we move right. So as x increases, does f of x increase or decrease? So we're moving to the rightward, we're moving rightwards along the x-axis. And the function f is only decreasing from here down to there. Right? Everywhere else it's increasing. So for decreasing, it's just a single interval. It looks like it's from -1 to 3, like this. Okay. So if you haven't thought about C and D yet, go ahead and pause the video now and see if you can answer those questions. Okay, so on what intervals is f prime positive? So for f prime, we're looking at this dotted graph here. That's the graph of f prime. And places where it's positive, I'll color those green. So where f prime is positive, we just want to know where is this dotted graph above the x-axis, because those are positive values for f prime. So that's here. We're above the x-axis here, all the way down to about there, it looks like. And then f prime goes negative, so we'll skip over this piece. And then f prime becomes positive again here, and it stays positive the rest of the way out. And like we did with f, we'll assume that the trends that seem to be established on either end of this graph continue. So where is f prime positive? It looks like from x equals -infinity, so all the way out to the left, up to, looks like this spot right here, which is x equals -1. And then it stops being positive. It picks up being positive again at 3. Well, not at 3. At 3 it's 0, but immediately after 3 it begins being positive. And then it stays positive all the way to the right, so to plus infinity there. And then again, we need to indicate that it's positive on both of these intervals, so that's a union operation to put these two intervals together. Right, on what intervals is f prime negative? Well, it's just this middle spot where it's sticking down below the x-axis. So that's from -1 up to 3. All right, now if you haven't thought about E yet, please pause and think about it. Okay, well, if you look at A through D, right, we've actually written the same intervals twice. Wherever the function was increasing, its derivative is positive, right? So f increasing is the same as f prime being positive. And then by the same token, wherever f is decreasing, f prime is negative. And you know, that's really not a coincidence, because when it, yes, this is right. When the derivative is positive, that means that the slope of the tangent line on the graph is positive, which means the graph looks like this. But if the graph looks like that, then it must be increasing. It's going up. And you know, same thing for, or a similar thing for negative derivative. If the derivative is negative, then that means the slope of the tangent line is negative. So the original graph looks like this, but that graph is decreasing at this particular point. So this isn't a coincidence that these things match up. This is always going to happen. So now that we have this idea in our back pocket, that the derivative is positive when the function is increasing and the derivative is negative when the function is decreasing, go ahead and have a look at the next page. All right, so here's a graph of g prime. So we are not looking at a graph of g itself, just g prime. So use the method you found to determine where the original function is increasing and decreasing. So we just said that a moment ago that g is increasing if g prime is positive, and g is decreasing if g prime is negative. So all we need to do is figure out where is g prime positive and negative. So for positive, it's positive here, and in this spot right here. So g prime greater than 0, g prime positive, that's the same thing as g increasing, and that's from minus infinity up to, it's hard to say exactly where this is, but let's guess that it's about a quarter. And then starting at 2 and up to, maybe it's 3 3/4. So from 2 to 3 3/4. That's where it's increasing. Now for decreasing, that's just where g prime is negative. So that's from here to here, and then from here all the way out to the right. So g prime is negative, where g is decreasing, and that's from about a quarter up to 2, and then from 2, no, not 2, 3 3/4 out to plus infinity, and a union there. All right, so if you haven't thought about b yet, please pause the video and think about it. Okay, critical numbers for g. Well, remember, critical numbers, those are places where the derivative does not exist or the derivative is 0. Well, the derivative exists for all real numbers on this graph, if we assume that this just keeps going down and this just keeps going up. The derivative of g has to exist because we are looking at its derivative, right? There aren't any holes in this graph, so the derivative must exist for all real numbers. So for our function g, there aren't any places where g prime doesn't exist. There aren't any holes in this graph. Okay, so that means we're looking for places where g prime of x is 0. And there are 3 of those places, right? These are just x-intercepts for g prime. But we can see where those are. There's one here, there's one here, and there's one here. So because we have the graph of g prime, we can find critical numbers for the original function g. So the critical numbers are at about a quarter, at 2, and about 3 3/4. All right, so for each critical number, can we tell, so if you haven't worked on C yet, pause the video. For each critical number, can we tell if the critical number is a local maximum, a local minimum, or neither? Well, let's take 1/4 as an example. Now remember, we don't know what the graph of g looks like, the original function g, but we do know that 1/4 is a critical number. So at the x value 1 over 4. We don't know what the value of the function is, so I'm drawing it as if it's positive because it's above the x-axis, but we don't actually know that. We do know that the slope of the tangent line there is 0 because it's a critical number. Okay, but also we know immediately to the left of 1 over 4, the graph is increasing. So that means immediately on this side of 1 over 4, the graph is going up as we move rightwards. So that means it's like this. Okay? And immediately to the right of 1 over 4, the graph is decreasing. So that means if we start at 1 over 4 and move rightwards, the graph has to go down, so like this. So we don't know exactly what g of x looks like near 1 over 4, but it has to be something like this. And is this a local minimum or a local maximum? Well, clearly this is a local maximum because we went from increasing to decreasing. Right? Okay, well now let's, and we went from increasing to decreasing because the derivative went from positive to 0 to negative. All right, well now let's think about this critical number at 2. So at 2, again, we don't know if the graph actually is above or below the x-axis or where exactly it is. I'm going to draw it as if it's here, but we don't actually know vertically where it's positioned. Immediately to the left of 2, that's here, the graph is decreasing. So as we move rightwards towards 2, the graph has to be decreasing. So it has to look something like this. At 2, the slope of the tangent line is horizontal, or the slope of the tangent line is 0 because 2 is a critical number. And immediately to the right of 2, the graph is increasing, so it has to be going like this. Well, this forces 2 to be a local minimum, as you can see. And in terms of the derivative, the reason that this happened is because the derivative went from negative, so went from less than 0. At the critical number, it was equal to 0. And then to the right, it was greater than 0. So you can see what's happening here is the derivative going through 0 and changing sign either from positive to negative or negative to positive, that seems to be determining whether we have a local minimum or a local maximum. So just based on, let's look at 3 3/4, and just based on how the derivative is changing, let's predict whether 3 3/4 is going to be a local min or a local max. So 3 3/4. We know that at 3 3/4 the derivative is 0. What about immediately to the left of 3 3/4? So that's going to be this interval, and g is positive there, or g prime is positive there. And then immediately to the right of 3 3/4, g prime is negative. So if it follows the same pattern as these other two, that means it looks like this one, right, where g prime is going from positive to 0 to negative. And so that means that we think that 3 3/4 ought to be a local maximum. Okay, well let's sketch a graph near this critical number. Of course, at the critical number 3 3/4, the slope of the tangent line is 0, so the graph is going to look horizontal there. Immediately to the left, the function is increasing, so it has to look like this. And immediately to the right, it's decreasing, so it has to look like this. And yes, sure enough, that does look like a local maximum. So we're kind of formulating a general rule here. The general rule is if the derivative of a function switches from positive to negative by going through 0, then you have a local maximum. And if it switches from negative to positive, you have a local minimum.